Okay, so now let's go over the chapter 4 worksheet together, part 1. First part is in regard to the electromagnetic spectrum. Question 1, find the frequency of a photon of light with a wavelength of 723 nanometer. So let's take and analyze the problem. We're looking for the frequency of a photon. Frequency is symbolized by nu. The unit of frequency are per second or hertz. And then we're given a wavelength of 723 nanometer, which means that the symbol for a wavelength is lambda. Here we have 723 nanometer. Remember that nano is 10 to the negative 9, so it's 723 times 10 to the negative 9 meter, or 7.23 times 10 to the negative 7 meter. Okay, let me just move this. Now, the formula we will be using is that the speed of light, c, is equal to lambda time, so lambda the wavelength, time nu the frequency. The speed of light, c, is a constant, so you should know it can be given to you as 3.00 times 10 to the 8th meter per second, or you might see 2.998 times 10 to the 8th meter per second. Okay, it's just a different way of rounding it. We are given the wavelength, so we're looking for, we are given the wavelength, so we're looking for the frequency. So let's solve this equation for nu. We have c equal lambda nu, so I'm going to divide by lambda on both sides, so my lambda cancels, and I get that the frequency nu is equal to the speed of light over the wavelength. Don't forget to write down units. The speed of light is 3.00 times 10 to the 8th meter per second over, and here you need to use lambda in meter because I have meter here. So 7.23 times 10 to the negative 7 meter. By doing it this way, the meter cancel, and I'm left with a unit that is per second, which is the unit of the frequency. Plug in this your calculator, and when you plug this into your calculator, you will get an answer to 3 sig fig as being 4.15 times 10 to the 14th per second, or hertz. And sig figs wise, I have 3 sig figs here, 3 sig figs here, so it makes sense that my answer is given to 3 sig figs. Two, while traveling through an intersection, you encounter a traffic light with a frequency of 4.30 times 10 to the 14 hertz. So this is here your frequency. Nu equal 4.30 times 10 to the 14 hertz, or second negative 1 is the same units. Okay, those are equivalent units. What color is the light? So we know there's 3 colors for the light. Either it's red, orange, or green. Okay, and the question is, should you stop, keep going through the intersection, or proceed with caution? Well, what you should know is the color is directly linked to the wavelength. Therefore, what we're going to be looking for, since we are looking for a color, we will be looking for the wavelength lambda. We're going to be using again the c equal lambda nu, but this time we are given the frequency. We know the value of the speed of light, which is given. So what we'll do is solve for lambda by dividing on each side by nu. So my nu cancel. Okay, therefore we're solving for lambda. and we get that lambda is equal to c over nu. C being the speed of light, 3.00 times 10 to the 8th meter per second. The speed of light divided by the frequency, so let's do this, over the frequency in per second, so 4.30 times 10 to the 14 per second. Okay, this is the same thing as second negative 1. My per second cancel, and I get an answer in meter, and plug it into your calculator, and you get 6.98 times 10 to the negative 7 meter. That's your lambda. Okay? Remember that your electromagnetic spectrum is given to you in nanometer. So we need to convert this number, this lambda, into nanometer. 6.98 times 10 to the negative 7 meter. Chapter 2, we're going to cancel the meter, convert to nanometer. Remember that where the prefix is, you always have a 1, and you will translate the prefix underneath on the other side of the division line, negative 9. Therefore, lambda in nanometer is equal to 698 nanometer. Look at the electromagnetic spectrum. This color is red. Therefore, I should stop. Do not forget to answer the question, okay? If you want to go back and check sig figs, you have 3 sig figs and 3 here. That's why your answer is to 3 sig figs. I still have 3 sig figs here. Remember that this conversion factor metric to metric is exact. So my answer should as well be given to 3 sig figs. So I have 3 sig figs all the way. Problem 3. A microwave has a wavelength of 1.20 centimeter. What is the energy? So we're looking for something new. The energy in joule of this wave. Energy. The energy is given to me by this formula. Energy is the Planck constant h times nu, the frequency. H, the Planck constant, per name is a constant, is equal to 6.63 times 10 to the negative 34 joule second, or you might have something more with more accuracy as being 6.626 times 10 to the negative 34 joule second. Okay, just depending on the accuracy. So here we're given the wavelength. So we cannot input the wavelength directly into this equation, but we know that C equal lambda nu and E equal h nu. We can solve the first equation for what we're missing, nu. So nu equal C over lambda. Okay, this is what we did in problem 1. Now what we're going to do, we're going to replace the nu here by this value. So by combining these two equations, we get that E equal h, but replace your nu by C over lambda. We have the value for lambda. We know the value of C, and we have the value of h. Okay? Now, remember that the speed of light is given to you as 3.00 times 10 to the 8th meter per second. Therefore, lambda has to be given in meter. We need to convert 1.20 centimeter into meter. So let's do this. 1.20 centimeter time, cancel the centimeter, convert to meter. The centi is the prefix, so I put the 1 here, and in the opposite line, I translate centi is 10 to the negative 2. Therefore, lambda is equal to 1.20 times 10 to the negative 2 meter, since my centimeter cancel. And we have the value of h, So we can just now plug in this. E is equal to 6.63 times 10 to the negative 34 joules second. Don't forget your unit always. C, 3.00 times 10 to the 8th meter per second, divided by lambda in meter, 1.20 times 10 to the negative 2 meter. Check that your unit canceled properly, the meter with the meter here, the second with the per second here. I'm left with joule, which is the unit for the energy. Plug this in your calculator, and to 3 sig figs, you get the energy being 1.66 times 10 to the negative 23 joule. And this will be my final answer. Sig figs wise, again, 2 sig figs here. This conversion factor is exact. 2 sig figs, no, sorry, 3 sig figs here, and a conversion factor exact, so I have 3 sig figs for the wavelength. 3 sig figs here, 3 sig figs here, and 3 sig figs here, so my answer is given to the least amount of sig fig, which is 3, as 1.66 10 to the negative 23. Now, let's take a look at the line spectra and the Bohr model. For each of these processes, indicate whether light is absorbed or emitted. Let's look at the first one. An electron moves from level 1, so the electron is here, and now the electron is moving from level 1 to level 5. So we're going from level 1 up to level 5. Just remember that around the nucleus, these level of energy increase. So when I go from the center of the atom to the outside, this represents an increase in energy. So to go from 1 to 5, I need to go to a higher level of energy. Therefore, the energy must be absorbed. B, the electron moves this time from 4 down to 2. So now I have more energy initially than I have finally, so I'm losing energy, and therefore the light will be emitted. Okay, for A, it was absorbed for the electron to jump from 1 to 5. For B, the light was emitted for the electron to jump from 4 to 2, go back to 2. What happens when an electron is excited, meaning that the electron goes to a higher energy level? The light will be absorbed. And on the other hand, when it relaxes, so relax means that it goes to a lower level, goes down, then the light will be emitted. 5. For each of these energy levels, list all sublevels that are present. Well, level 1, we only see the S sublevel. In level 2, we see S and P. Level 3, we see S, P, and D. And for level 4 and above, we see S, P, D, and F. There's 4 different sublevels. S, P, D, and F. Energy-wise, S is lower in energy than P, lower in energy than D, lower in energy than F. Now, indicate whether each of these level-sublevel combination is possible. We just stated that on level 2, we can only have S and P. Therefore, there is nothing such as a sublevel D on level 2. Level 3. If we look, we stated that in level 3, we find S, P, and D. Therefore, there's nothing such as 3F that exists. On level 3, we can find the S, P, and D sublevel. Therefore, this sublevel does exist on level 3, and this combination is possible. When we write this combination, what we do is we write the number first, followed by the letter. And this is how you represent the combination level sublevel. The 3D does exist. Complete the sketch below to show the filling sequence for silicon, then write the electron configuration for this atom. Identify the valence electrons. Well, we're going to do way more than silicon. We actually will do lithium, we'll do carbon, and then we'll do silicon. Okay, so we're going to do this for carbon and lithium and silicon. These diagrams are electron diagrams, so we're going to fill up the electrons, assuming that these atoms are neutral. Because lithium has an atomic number of 3, if the lithium atom is neutral, we will need to place 3 electrons. Atomic number of carbon 6, neutral, 6 electrons. Atomic number 14 for silicon, 14 electrons. So to fill, we're going to fill from the bottom to the top, 1 electron at a time, following the 3 rule, Hausbau principle, Pauli's exclusion principle, and Hund's rule. I need to place 3 electrons for lithium. I'm going to first put an electron spin up. An electron is represented by an arrow. Then because this level is not full, I'm going to complete with a second one, spin down. And I'm going to place my 3rd electron on the level 2s. Therefore, my electron configuration will be written as 1s2, 2 electrons in the 1s sublevel, 2s1, 1 electrons in the 2s. So this one was for lithium. Let's do carbon. We need to place 6, spin up, spin down for the first 2 electrons, 3, 4. And now when I'm going to fill the 2p level, I have to spread them, okay, before I can pair them up. So now I place 6 electrons. When I'm going to write the electron configuration for carbon, it's going to be 1s2 because I have 2 electrons in the 1s, 2s2, 2 electrons in the 2s, and 2p2 because I have 2 electrons as well in the 2p. Let's do silicon following the same filling up rule. 1, 2, 3, 4, 5, 6, 7. I spread them out first. 9, 10, 11, 12, 13, 14. What did I miss? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and my bad, 14. Spread them out in the 3p orbital. And my configuration will therefore be silicon 1s2, 2s2, 2p6, 3s2, 3p2. We need as well to identify the valence electrons. What do we call the valence electrons? The valence electrons are located on the outermost energy level in the subshell, sublevel S and P only. So here, the outermost energy for lithium is 2, and my valence electrons are located right here in the 2s. So I have 1 valence electron. For the C, the outermost energy level is 2, and I have 2 sublevel here that have electrons. Therefore, these 4 electrons are the valence electrons. For silicon, the outermost is 3, and in the 3 energy level, I have electron in the 3s in the 3p. I have 4 valence electrons. So therefore, lithium has 1 valence electron, carbon has 4 valence electron, silicon has 4 valence electron. What you are asked to do in problem 8 is to write the electron configuration for each of these atoms and then identify the valence electrons. We already did lithium, so I'm not going to do this again. Lithium is 1s2, 2s1, with here the valence electrons. For magnesium, we need to place, so it's up to you. You can just like use another of this orbital diagram, or just use your knowledge of the periodic table to write this configuration. Magnesium will be 1s2, 2s2, 2p6, 3s2. The higher the outermost energy is 3, and on this level 3, I have 2 electrons in the 3s, so 2 valence electrons. For neon, I need to place 10 electrons. Therefore, I'm going to have 1s2, 2s2, 2p6. The outermost level of energy is 2, and I have electrons in the 2s and in the 2p for a total of 8 valence electrons. And if I do sulfur, sulfur has 16 electrons, 1s2, 2s2, 2p6, 3s2, 3p4. The outermost energy level is 3. I have the 3p and the 3s, so these electrons, the 2 in the 3s and the 4 in the 3p, are valence electrons. Lithium has therefore 1 valence electron. Magnesium has 2 valence electrons. Neon has 8 valence electrons, and sulfur has 6 valence electrons. What I want you to pay attention to now is take a look at, you remember the group number that we talked about? This is 1A, this is 2A, this is 3A, 4A, 5A, 6A, 7A, and 8A. Well, take a look at lithium. Lithium is here, located in a group 1A, 1 valence electron. Look at magnesium now. Magnesium is located in a group 2A, 2 valence electrons. You start seeing a trend. Neon, here in the group 8A, well, guess what? 8A, 8 valence electrons. And let's do the last one, sulfur. S is located in the group 6A, 6 valence electrons. So you can see how important is the periodic table and how important it is to know how to use the periodic table. We have 2 more to do. What about carbon and silicon? Well, they both are located in the group 4A. Therefore, they both have 4 valence electrons, and therefore they both will have similar behavior because they belong to the same group, to the same family. Thank you, and have a good one. Bye-bye.